Hello, this is my second video proof for my topology class. And for this proof, I chose two problems that are very related from the worksheet that we did that one session in class. I picked problem 17 and problem 18. Problem 17 states that if A is a finite subset of R, then the interior points of A equal the empty set, and the boundary points of A equal the set itself. In 18, if A is a countable subset of R, then as well the interior points of A are the empty set, and the boundary points of A equal the set itself. Now, using the fact that all finite sets are countable sets, I'm going to answer both of these questions with the same proof. So I'm going to prove it for all countable sets, and then that should take care of 17 as well, because finite sets are all countable sets. So the main thing that we want to use as an idea here in order to base a proof of is that, first of all, the subset R, the set R of all the real numbers is uncountable. This essentially means that in between every two elements of the real numbers, there's also an uncountable amount of elements in this subset. For example, if we took the open set between 1 and 2, then there's an uncountable amount of elements or numbers that belong to the real numbers here, so that any countable set that included 1 and 2 would not include, by definition, everything that lies in between 1 and 2. Because if you add something that is uncountable to a countable set, then therefore by definition you cannot count it anymore, so it's uncountable. So using this idea, what we want to show is that if we have a set A that is a countable set of the subset of R, and because of the idea that I just showed you, it means that if A, for example, equaled the integers, then that would mean that if we go to the number line and we have -1, 0, 1, and 2, and that's our subset, then in between every number that belongs to our set, there's an uncountable amount of numbers that belong to the real numbers. So now, if we want to check what the interior points of A are and what the boundary points of A are, then obviously we have to start the definition of both of these things. So now, something is an interior point of A when that point X that belongs to A lies in between, like you can draw, let's say you have this number line, right? Again, which is not necessarily a number line, but is a line with the elements of A. Then every interior point of A you have to be able to draw an open set around it that includes the point itself and some other point in the set that one would only be an interior point in this case if A equaled the integers, right? And we had 0, 1, 2, then 1 would only be an interior point if we are able to draw a set around it that includes 1 and another element before getting to 0 or to 2 that also belongs in A. Now, because of the idea that we mentioned at the beginning, that in between any two elements of the real numbers, there's an infinite amount of uncountable smaller numbers, then this means that if we have a countable subset of R, then there's always going to be some space in between every single element of A of infinite smaller elements that belong to R that would not belong to A. So again, if A was the integers, then we can draw an open set around 1 of 1/2 and 3/2. Now all three of these numbers belong to the real numbers, but only one belongs to our subset of the integers. And this idea applies to any countable set, because if your countable set is a subset of the real numbers and it is countable, then it has to have an area in between those two values that overlaps with the real numbers, but that area, because by definition, cannot be included in the countable set because that area is uncountable. Therefore, our definition of an interior point, which is again that an element in A, in this case our element is 1, we should be able to draw an open set around this element in which there's at least another element different from this X that is also included in A. So we should be able to write an open set that looks like X comma Y, where Y also belongs to A. However, we cannot do that because if we wanted to draw an open interval from 1 to 0, right? And we wanted to say that Y is 0 and X is 1, and therefore both are included and they both belong to A, therefore this is an interior point. We also come across all these points in between them that exist within this open set but are not elements of A. All the numbers in here are elements of R because R is continuous, but these numbers in between are not elements of the countable set A. Therefore, we cannot find any interior points of A, so that the interior points of A are only the empty set. Now, the boundary points of A is sort of like the opposite of the interior points. So the definition of a boundary set of A is that if we are able to draw, again, I'm going to draw my number line so you understand the idea of what I'm trying to say. Then, and we have 0, 1, 2, for example. Then the definition of a boundary point of A tells us that you should be able to draw an open set around your boundary point that also includes a point of the complement of our set. Now here, since A is a subset of R, then A complement is equal to R without A. So everything that remains in R after we've counted A belongs to A complement. Now, again, going back to our idea from the beginning, we know that a quality of the set of the real numbers is that in between any given element, it could be 1 over 1 billion, it could be 1 over, it doesn't matter how small it is. You can always find even smaller numbers around it that are infinite and uncountable. Therefore, in between every number that we include in our countable set, we can draw an open set that includes another point that does not belong to our original A, but is still part of the real numbers, meaning that it's included in the complement of our set. Therefore, kind of in an opposite way of how the interior points of A worked for this case, then all of our elements in our set A will be boundary points, because in between every countable element of a subset of the real numbers will have elements in between that are uncountable. Therefore, we have proven that if A is a countable subset of the real numbers, then it has no interior points other than the empty set, and all of its points are boundary points. And since we also said that finite sets are a type of countable sets, then by proving number 18, we've also proven number 17. Thank you.